Now we're going to talk about the penalty method. In the penalty method, we associate new unknown, which is our tau n, in the normal direction, with the old one, which is our displacement solution. Here is related to our gap function g. So in a normal direction, we try to associate tau n as a function of g, our opening. In a simple case, we can relate it to linearly by a so-called penalty stiffness, which means that as there is overclosure, so which means the gap becomes negative, the Tn, which is a normal direction pressure, becomes larger. We could also define a nonlinear function, a more smoother function for Tn. So this way there is a one-to-one correspondence between G, which is our opening, and Tn. So effectively we expressed our unknown Tn with our previous unknown displacement solution, and we remove Tn from the list of unknowns. In the tangential direction, we could apply the same trick. So previously this Ts is undetermined for tau between -1 to 1. Now we can write Ts as a function of tangential direction opening, multiply with some penalty stiffness k. So on this plot, on the plot of tau versus us dot, then this relationship will be represented by a straight line. So again, there is one-to-one correspondence between the opening and the tangential stress. Of course, we can also use a smoother function to relate it to. The advantage of having a smoother relationship instead of just a simple linear one is that at this corner we have a much better transition zone. Numerically, this is more stable than a sharp corner, because here along this part of the curve the solver could find a continuous change of gradient, while at this point the gradient is undefined. So starting to the left you have a very large gradient, on the right of it you have a zero gradient, and this is always bad for convergence. So the final finite element equation with the penalty method can be simply represented by expressing Tc in function of our displacement u. Once we relate Tc with u, we can then start our discretization process by finite element method. By that I mean that I represent our solution variable u in terms of shape function n multiplied with degree of freedom vector a, and the variation of u would be shape function multiplied the variation of degree of freedom vector. So we can plug in, and eventually after many steps of derivation we can arrive at a familiar expression where on the left we have variation of a multiplied with the internal force vector, on the right we have the variation of a multiplied with the external force vector, and this is the additional term, which is the variation of a multiplied with the contact force vector, and this force vector is a function of a, because we have gamma c as a function of a displacement solution, which we need to search for in every iteration. We also have the Tc being a function of u, and u is a function of our degree of freedom vector a. So we have the contact force vector being a function of a. So we remove the common terms on the left, the variation of a, we arrive at this simple expression of equilibrium. And we can represent our residue by minus the f internal and moving it to the right. And as before, we can then take the partial derivative of this residue vector with respect to our degree of freedom vector and obtain our tangent stiffness matrix. Now our tangent stiffness matrix has the Euro term, which is partial of f internal with respect to the degree of freedom vector, and this additional term, which is contact stiffness. So this is stiffness arising from the contact stresses.